Okay, so this is going to be the first part of chapter 2. Hopefully this is going to get us back on schedule, and then we will pick up with section 2.4 on Wednesday. Okay, so you're going to see there's learning objectives in the beginning. There should be 2 slides of learning objectives, but what we're going to talk about is elements, atoms, and the periodic table. Okay, so it's kind of a review for anybody who's had maybe high school chemistry, so hopefully it won't be new. And I'm going to apologize for the photos. I'm trying to take them on the tablet, and you can see I've got 1,000 things around some of the photos, but hopefully they're not too distracting. Alright, so here is our second slide of learning objectives. This is for the entire chapter though, okay, so we won't cover all of them today. So starting off in 2.1, these are examples of different types of samples of elements, and you can see they look very different. And so elements are going to be really the smallest atom that retains its property. That retains its chemical and physical properties. So chemical property, physical property. Okay, meaning if it's solid, it's solid. If it's crystalline, it's crystalline. But they all look very different. So in the end, there are 118 elements, but I think we're up to, it might still be 118, but for some reason I feel like it's 122 known elements now. I'll have to double check this. And so in the universe as a whole, the most common element is hydrogen, followed by helium. So hydrogen is element number 1. Helium is element number 2. Hydrogen exists as hydrogen gas, like this, and then helium exists all by itself, and this is what we use to inflate balloons for parties, okay? And they float up into space when we let them go. So the 2 most abundant elements are hydrogen and helium in the entire universe, okay? So not just Earth, but the spirally galaxy of the Milky Way. Now on Earth and on the human body, you're going to see that there is a little bit of overlap, which I just find this completely fascinating. Because if you look at the elements that are the most common on Earth, it's oxygen is first, and then in the human body, it's oxygen. And I just think that that's a really, really unique thing because we need it to breathe. And the Earth has the most. And Earth actually is one of the only planets that has oxygen. This does not look like planets, but this is Earth for humans to live on, right? Now there are some other similarities, but the human body is made up of things that we don't find as much, like carbon, and calcium and phosphorus, fluorine. Some of these are minerals, okay, that our bodies are made up of. And a lot of this is what goes into making rocks and gemstones, okay? But the one thing we share in common is that oxygen is the number 1 element. And for Earth, it's like 46%, and then for the human body, it's 60%, I think. It's so tiny on here, I can't see, but 60%. So, a lot. Now, these are the most commonly used elements names with their symbols. We have a periodic table on our board that only has the symbols, no names. However, on the test, I will give you, excuse me, a periodic table that has the symbols and the names. Okay? In fact, we're going to fill one out shortly in this chapter, and then you'll have one that's ready to go for exam number 1. Alright, so atomic theory is important to us because it really tells us, well, there's the old atomic theory and then there's what we call the modern atomic theory. And modern atomic theory is that the fundamental concept is that all elements are composed of atoms. So when I have, let's say I have a lead pencil, right? And we know that at the end of this lead pencil, there is some sort of writing material, whether it be lead or carbon. But if it's a lead pencil, it's made up of a bunch of teeny tiny lead atoms. Okay, so I could break the pencil apart and theoretically get smaller pieces of lead. And same thing with the carbon or the graphite. Okay, so it's made up of tinier atoms that are all carbon or all lead. But most elements in their pure form exist as an individual atom. Okay, so that's just kind of a part of the modern atomic theory. And then, so things like carbon, lead, gold, silver, all exist by themselves. But there are a group of elements that can't exist by themselves, and we call them diatomics. Okay, so let's break that word apart. Di is two atoms. Okay, so these would be called monoatomics. One atom. Okay, so the ones that tend to exist as two are hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, and iodine. So look at their location on the periodic table. With the exception of hydrogen, you're going to find that they're all in the upper right-hand block of the periodic table. Okay, and we'll talk about hydrogen as we continue on in this chapter. Alright, so the structure of atoms. This is a lot of what came out of the few studies done by some scientists over the last probably 200 years. And so Dalton's atomic theory is kind of the, I guess, the precedence for what we understand. When Dalton published his atomic theory, people thought he was crazy because it just didn't make sense, and there really wasn't much science, experimental science, backed behind it. A lot of it was just theory, hence the word theory. But then some scientists came along and proved a lot of what Dalton said was true by using experiments. Dalton's theories with experiments. And we'll talk about the most significant ones. Okay, and so this came back probably, a couple hundred years after Dalton's gone and supported Dalton's theories, but not all of them were held to be true. He has a total of 5 postulates in his theory, and we hold 4 of them to be true today. Okay, so minor but important modifications were made, which considered atoms to be indivisible. Okay, because that was one of his theories, is he said atoms cannot be further divided. And we know now that that's not true because of some of these divided. We know now that atoms are actually composed of electrons, protons, and neutrons. Okay, so electron, proton, and neutron. And each of the particles is a little bit different from the other. So the electron has a negative charge, hence my negative sign. Proton has a positive charge, and a neutron is neutral. Okay, so this is the 3 subatomic particles that add up together in different ways to create atoms, which we have 118 of them, 118 different elements. So we have 118 different arrangements of electrons, protons, and neutrons. Okay. All right, so here are some properties. This is a good table to know. I would know the first, the second, and the last one. And what I'm going to tell you is I'm going to describe the relationships. So protons and neutrons are roughly around the same mass. Okay, pretty close. Electrons are teeny tiny. Okay, if you thought about a football field, like a huge football arena, the electron would be the size of the football in the center. That's how tiny an electron is, if we could blow it up as big as the outer parts of an atom. Okay, so the mass is very small. Protons are positively charged, electrons are negatively charged, so they are sharing that in common, whereas neutrons are neutral. All right, so one of the experiments that was really important is called the metal foil, or sometimes it's called the gold foil experiment. And what happened was he took a laser beam and shot it through a piece of gold paper. And what he expected to see was he had like this photo developing device where whatever came through would develop on this paper, and he could study the inside of a gold atom because of what was being deflected off onto the gold paper. So what he proved in this experiment was that in each atom there is a core. And at the core are protons and neutrons, okay, and they exist together. And then in the outer part is where the electrons exist. And they don't exist exactly on these circular bands, but for the sake of science, we just kind of simplify it this way. And so what Rutherford said was that really most of the atom, the gold atom, is empty space, right? Because we said, or empty volume, because we said electrons are so tiny. So if we're shooting laser beams through an atom, electrons are so tiny it's very unlikely that they're going to hit. Now, every once in a while, he saw that one of the beams would get deflected back at him. Okay, so it would come here and go back. But then he also saw that some beams would come in and they would get deflected. Okay, so they would come through and they would deflect, which meant that those beams were hitting something that was very dense. Okay, I don't know what happened. See if I can start where I am. Okay, which meant that there was a very dense core. Okay, and the dense core we know is where protons and neutrons existed. We call these the nucleons, right? So the reason why we call them the nucleons is because that dense core is called the nucleus. Okay, so in the nucleus, nucleons are there, which are protons and neutrons. It's a dense core, and the empty volume and space on the outer part of the nucleus is where the electrons exist. Okay, so like this says right here, most of the alpha particles went straight through the empty space. A few particles were deflected, and then very few ricocheted back towards the source, which meant that the nucleus was much smaller than the actual volume of the gold atom. Okay. So it was a very important experiment, and I can't remember the exact date, but it was roughly in about the 1800s that we had this discovery. And there were a few more before that. You might see the Millikan's oil drop experiment, and where he discovered the charge of the electron, the actual value of it. And there is the plum pudding model. So there's lots of different experiments that you will have maybe learned about before, but this is one of the most significant because it tells us the actual arrangement of an atom. At least it gives us a theory, right? Because we don't actually know it. This is all theorized. All right, so here's a little bit better of an image of that deflection. Okay, now in your textbook, this should probably be figure 1.4 because in version 1.0, this is chapter 2. In version 2.0, this is chapter 1. I should have said that on the first slide. I'm really sorry. So hopefully you're not too confused. All right, so a more modern understanding of atoms is that, remember I told you that planetary-like structure where the electrons orbited around it? So even though I drew it like that, they don't exactly orbit like the planets do around the sun, okay? But they do occupy a certain space or a certain region around the nucleus, but it's not an orbit like you see around the planets, okay? So it's a simplification or maybe a model of atomic theory, but it's not exactly true. Okay, so what it really looks like is this mess right here, okay? The nucleus is the dense part in the center, and you can see all the electrons are kind of out there around, but they're not traveling in elliptical or orbital paths, okay? So this is going to hopefully get us fairly caught up for chapter 2. I don't want to go on to the next section because we're going to start with a skill building exercise, and I want to do as many of those with y'all as I can. And then hopefully we'll finish chapter 2 or get really close to on Wednesday, because I promised you guys some time for chapter 1 homework, and I don't want to make a liar out of myself so early in the semester. And so this is my hopes that on Friday we will have time for that. Okay? Please email me if you have any questions. I apologize for missing your lab today, but I hope that things went well with Dr. Ladine, and please email me if they didn't or you have questions or concerns. I should be back in the office tomorrow.